we needed to attach this, the scientist came to me, I needed to attach this assembly to the back of the telescope. Just need a bracket. Easy stuff, right? But it has some complicated requirements. It has some basic stuff like, it has a bolt pattern here, it needs to match up with a bolt pattern there, but it actually has some pretty severe loads. The way these things work is they actually get cut from the balloon and then plummet, and then a parachute catches them, and then you reuse them. So it's cool for the reusable, but that parachute shock is a lot of load. And it also has to be very, very stiff, because there's a cryocooler nearby shaking, and if it couples in with that, it's going to blur your image and affect your science. And because these balloons are really limited in what they can launch, it has to be lightweight. So, here's how, and you guys are really going to be familiar with this. Here's how a typical human solves the problem. And this is one of our best. This is this guy, Drew Jones. He laid out the James Webb Space Telescope and is currently laying out the Habitable Worlds Observatory, which is NASA's next big mission. And I got him, because he thought he was going to retire, to make this CAD model for me and compete with AI. He was the only one willing to do it. And when he designed this, it was stiff enough, easy to manufacture, but I don't know, there was a miscommunication. It was way too heavy, didn't meet the mass target. So he came up with another iteration, and here he did what you would expect. He just pocketed it out, right? That's what people do. A lot of sketching and extruding, but he's like wicked fast at that kind of stuff. And in this case, he got the mass down, but it didn't meet the stiffness requirement. And maybe he didn't quite understand how big it is, because those pockets are actually not very good. They're hard to reach. Wasn't a very machinable part. I said, Drew, make it stiffer. He added some mass back, but now it doesn't meet the massive stiff or machinability requirements. And I'm like, okay, Drew, I was doing the FEA, and think of something different. So he came up with this, kind of crazy looking thing that actually does meet the mass and stiffness requirements, but it's pretty unmanufacturable. I think even like if you were printing it, it would be really hard to get the supports removed. So we wanted something better, right? Like Drew and I, we probably could have spent a couple weeks and come up with a solution, but having two highly skilled engineers spend weeks on a balloon bracket is not a good use of our time. So Evolved Structures, it's basically like topology optimization with a layer of NASA requirements put on top of it. So you just have the preserves, the areas you have to keep, red, the areas where you can't have material, and you have loads and manufacturing constraints. And those are pretty quick to define. These are just simple geometric shapes, and they are fully determined by NASA requirements and processes. And then you just evolve the optimal design using generative design AI tools. In this case, it's Fusion 360. And you've got a CNC design here, and then an additive design on the other side. And then you just build them with digital manufacturing. So bracket solved. So we can accelerate going from requirements to parts. So what took 2 engineers 2 days and really hustling, doing 4 iterations, one AI-powered engineer can do over 100 iterations in an hour and come up with a design that's lighter, stiffer, stronger, and more manufacturable. And this affects science. That stiffness is really key to not blurring the image. So these are science-enabling designs. I think, if you haven't seen this, you can go ahead and pass it around, Dwan, if you like.